Our last talk for the day is something I was personally looking forward to, and this is an interesting talk titled "Quantum for Combinatorial Optimization Problems." This talk will be delivered to you by Dr. Arun Sehrawat, and Dr. Arun Sehrawat is currently a quantum research scientist at QPI Bangalore. He he acquired his PhD in quantum information and computation from the Center of Quantum Technologies, CQT, National University of Singapore, NUS. Following this, he had stints as a postdoctoral fellow at NUS, the University of Guadalajara, Mexico, Isa Mohali, uh, Harish Chandra Research Institute, where he worked on problems in quantum measurement, quantum computation, quantum information theory, and optimization, amongst others. After his 10 plus years in quantum computation research, he has recently delved into the field of artificial intelligence with QPI. Dr. Arun Sehrawat, the pleasure to introduce you is mine. The screen is yours.
Yeah, thank you so much. So, am I audible? So, am I audible?
Yes, sir, you're audible. Yes.
Okay. So, thank you so much.
Also, you may continue till 5:10, since the previous talk extended. You may continue till 5:10.
Okay. So, I have not practiced my talk, how long it will last, but I will certainly finish before 5:10. And thank you so much for giving me this opportunity to present some of our work here. And so maybe I can share my screen or something. Yeah.
Yes, sir, you may go ahead.
Just a sec. Okay. So the screen is visible, right?
Yes, sir.
So I will. I want to do like this because in this way I can write a little bit like this. You know? So is it okay if I go like this?
Oh, yes, it's totally on.
Okay. So thank you so much. And so today I will talk about quantum for combinatorial optimization problem. And so let's start. So traveling salesman problem is one of the most famous combinatorial optimization problem, right? So I just describe here, straight to the point, one of the famous problem which is very difficult to solve, and I will tell you why. The problem is, suppose you have n number of cities, right? And this n is, in this case, is 15. So you have n number of cities, and this is your input map. So for each city, you have x and y coordinates, right? So city 13 is like at 4 and 0, like 0 and 4. So, and then you give these coordinates, and then you have a salesman who start from one place, right? And then he has to travel all these 15 cities, right, at 15 different locations, and locations are given by these coordinates. And so maybe it start from 6, right? It may go to 3. Then there will be distance between 6 and 3, right? It may go to 2. It may go to 14, right? So everywhere there is a distance d6 and 2, right? And which you can compute by taking these coordinates, right? Distance between these two coordinates, x and x prime and y prime. So there is a distance here. Function of these two coordinates, two places, right? So you have, this distance can be the cost to travel from city U to V, and which is a positive number. You can take a Euclidean distance if, or you can walking on the globe, then you can take, or you can take from Google Map, like from one place to another place you want to, right? And then you have a time step. So this is T is a time step. At first time step, you are at the city 6, and the next time step t is equal to 2, you may be at 3 or maybe 2 or maybe 14 or maybe one of these, right? So this is t2 and t3, and after completing the full round you must come back to this sixth place. So there will be complete round of these cities. So that is the problem. So one person has to find a complete round and to make a complete round. So there can be many possibilities, because from 6 you can go to any of these cities, right? And then from 3 you can go to 4, right? You can go to 8 and you can go to 7, right? There are many possibilities. Because of these many possibilities, right, so it is very difficult to find optimal solution, right? So how we describe the problem? So this is one way of describing the problem. So you can take a decision variable at time t, and like you are at the node u, right? For example, I choose that at time t is equal to 1, I am at the 6th node. So z of 1 and 6 will be 0, no, will be 1, right? And z of 1 and u, which is not equal to 6, will be 0. So this is a decision variable, right? And then you can combine these decision variable, because you are taking step t to t plus 1, because and you are moving from city u to v. So this is a, you take a product of these. So if you are at time t, you are at the city u, and at time t plus 1 you are city v, then this product sum over all t will be 1, and then you take corresponding distance. So this c is basically this d distance, or cost, or any kind of cost. You can take like a maybe, distance is a good measure of cost, because suppose you have a constant speed, and then the amount of petrol you it goes with that is, the cost is kind of proportional to the distance traveled, and then you have a total cost. So you have to minimize this total cost, and so you have to find this value of this decision variable, which defines the path, right? And you have so the problem is to minimize c with this constraint, and this means that at node u, at city u, you have to must visit at you must visit it once, right? So you cannot visit city twice. So you cannot go like this and then come back city 9, and then this kind of loop is not, this is not allowed, right? So you cannot visit a city twice, you have to visit it once. And then second constraint is that salesman at each time it must be at one city, right? Of course. And then you have to sum over these, and these two constraints you put, and you minimize this one. And such a problem is called combinatorial optimization, because there are many combination possible, as I showed you, that you can from 6 you can go to 3 or 7, 3 or 2 or 14, right? And so these matrix of these this z matrix, which is of this small z tu, right? So matrix of these will be our solution, and each of them can take two values. So for 15 city we have to take that many possible solutions exist, right? So you can clearly see that a human being cannot do that, right? Even computer cannot do that to find optimal solution. That is why it is called NP-hard problem. So there is no polynomial time algorithm exists which can give you, optimal answer, right? So, but there are methods to find a non-optimal answer, which is close to, which is, like there are proofs, theorems, which says that the answer should must be close to the optimal one, right? So I will describe one of the two of such solutions. One is classical, another is quantum. Okay. So I go next. So this is one of your optimal solution. So you can start maybe from 6, then you go to 2, and then 14, and then 1, and then 15, and this is, this is one of the solution, right? So this is an output map. Okay. So so this is the solution, and then and you can find many NP hard problem, and this kind of formalism is called icing formalism, because this variable can take 0 or 1 value. You can think as a spin variable, which can take spin up and spin down variable values, right? Spin up and spin down. So such kind of formalism is taken from this paper, and there are many different problems are described using this formalism in this paper, which are NP hard, right? So you can, for further detail, you can look here, right? So let me start with the first solution, simulated annealing, right? So you can look at this paper. This is kind of a review for simulated annealing. As I told you, the solution matrix will be this Z, right, which is made of these binary variables. It's a n cross n matrix, and they must satisfy these two constraints. So, and this is the total cost. You have a distance, or you can call it cost, between city U and V, and then you have decision variables, which says that at time t you are at the city U, and t+1 you are at city V, right? So, and this is your total cost. So simulated annealing basically works like this. So you maybe start with some number of iterations. Maybe it's a iterative procedure. So let's fix maybe 100 iterations, right? And let me tell you a bit about this annealing. Annealing is a metallurgical process where you want to remove the strain in a metal. So what you basically do is you just heat it up really high and then slowly cool down. So that process is called annealing. So here the same thing is that you take a very high temperature. T initial is very high, much higher than T final final temperature. This is almost close to 0, let's say, right? Or you can choose a little bit more than 0, and then you just take these gamma steps, right? So you start with the T initial, and then you go T initial minus gamma, and then T initial minus 2 gamma, and so on. And then you just take these steps and such, and then you take this 100 steps, right? You just cool down the thing in 100 steps, and at the first step you start with some random solution, right? Some random solution, and then you keep updating your solution, right? And this is the procedure to update your solution. So this is the procedure. So let me, the step 2 is you pick a new solution in the neighborhood of Z, right? So your initial solution, because you take a first initial solution, then you store it as your solution, and then T is T initial. And then next step, you take a neighborhood of this one. And this process is called Markov chain, right? You just take what is your previous step, and then take the next step based upon the previous step, right? So suppose, and then this new Z, right? You check whether the constraints are satisfied or not, right? These two constraints. If yes, then you compute the cost, right? You compute the cost using this formula, and if the cost turn out to be smaller than the previous one, then of course you are happy, and then you will accept it. So delta is a change in the cost. Delta is negative, that is cost is decreased, then you are happy, and then you accept Z as a solution, and then you update Z sol as your new Z, right? New Z as Z sol, right? If the cost is high, like for example, you maybe goes in that one direction where the cost become higher, but then you accept solution Z with this probability, right? So you know that exponential is this, right? E raised to power minus x, and this is x, and this is 1. So when this temperature is high, then this quantity is very small, right? X is very small. So let's say x is delta over t when t is very high, right? Initial phase, right? Then chances of accepting the new solution is quite high, right? And because you want to jump local minima. So this second part, right, when the cost is higher, and this is kind of, there is a bump, right? You may want to jump this bump, and then you say, okay, we accept it. Maybe we find a good minima on this side because we are on this side. So you jump, right? And as temperature is decreasing, as it becomes smaller and smaller, so the probability of accepting new solution is less. It gets accepted only when the cost really decreases, right? So that's how this is the second step. It's called metropolis. This, like in metropolis algorithm, such step is also involved. And then basically you repeat this second and new step. You generate a new solution, check the cost is reduced. If it reduced, you accept it. If it is increased, then you accept it with this probability, and then you repeat this 100 times, and then whatever you get in the end, you call it solution. And the cost is, this is simulated annealing, right? And so you will get something like this. So now this I showed you the solution for n is equal to 50. So n is equal to 100, right? You have something like this is an input graph. So traveling salesman has to travel these 100 cities, right, which is on this globe given by x and y coordinates, right? And then you start from some random configuration, and then you go on, you run the simulated annealing, and then you see this this cost is decreasing. And you are proposing new solution. So each new solution is represented by these green points, right? And then the solution which are accepted, they are represented by blue points. So see, the sometimes cost is increasing, sometimes decreasing. So you see, this is like you are accepting the solution even when the cost is increasing in steps, right? And then finally you get this is your solution, right? And you can see that this is almost I don't know 60 to 70% reduction, right? So using this one, you start with a random guess and you get a solution which is better than the random guess, and this, your solution will look like this, right? So this is simulated annealing and input and performance, and then this is the output map, right? So now I will describe you about quantum annealing. So quantum annealing is based upon the same similar procedure. So what quantum annealing says, it's prepare the system in ground state of this Hamiltonian, or this operator, like, and this ground state is a superposition of all the possible states. So each state is a solution. Means each state is Z, right? So each state is Z solution, and which is basically Z. And then this ground state of this Hamiltonian is superposition of all the solution. It is like when the temperature is very, very high, then our simulated annealing take everybody, can move from one Z to another Z, right? So it's kind of considering all possible Z, right? So the same way, you are taking a superposition of all possible solutions. Solution is this Z matrix, and which is like you prepare your initial state in this H initial, which is superposition of all these solutions, right? And this is sigma x is a Pauli operator, which is this one, right? And because you replace here each Z tu with sigma tu, right? So each decision variable, which can take two values, is replaced by spin, right? So you have n square decision variables, right? And which means you have, like I showed you 15, in case of 15 raised to power 2 is a 2 to 5 spins you need to run this procedure, right? Rather than so that's why people say this is the quantum computation is perform better, because it's don't take that many bits, but it takes that many qubits, because of this exponential factor. This is the number of bits you don't take that many bits, but you take that many qubits. That is the power of quantum computer, right? Because of this exponential part. So you take only 225 spins or qubits and to run this algorithm, right? And so basically you change decision variable to a spin operator sigma x, right? And then you prepare at the first step you prepare your system in ground state of this Hamiltonian, which is an equal superposition of all those states, is equivalent to the temperature is infinite. When temperature is infinite, each state is equally probable, right? Now then you slowly decrease that then you take this Hamiltonian, right, which is a combination of H initial and H final, and this tau is your control parameter, and you at the place of temperature we have now tau, which is a Hamiltonian parameter, and you slowly change this parameter from 0 to 1. So when tau is 0, then H is H initial, and then tau is 1, then H is H final, right? So you go from H initial to H final, and then slowly means adiabatically, and adiabatic theorem says that if you go slow enough, right, from this 0 to 1, then the system stays in the ground state, right? So you start with this ground state of this Hamiltonian, this H initial, and then you goes ground state of this final Hamiltonian, right? And the ground state of final Hamiltonian is the solution of your problem, right? So you write your final Hamiltonian in such a way that the ground state of this final Hamiltonian is the solution of your problem, right? So you go slowly, system stays in ground state through evolution, and then you get the final ground state of final Hamiltonian, and then you measure the ground state, and that will be your result, right? But you know, this is called adiabatic quantum computation, step 1, 2, 3. Now step 4, because when we perform experimental setups, things are not very you know, ideal, and there are real life situations, so you have some noise and things like that, which you cannot perform this adiabatically, you know, very nicely, and this adiabatic evolution is difficult to perform in real life. So what you do is you repeat this whole procedure 1, 2, 3, maybe let's say 100 times, and then each time you measure result, and then from that you can estimate your you know, what is your final you know, answer to your problem, right? So most likely you will get all the times this ground state, right? So that is the quantum annealing, right? So basically, let me repeat it. You change the decision variable into spin operator sigma z, right? And then you prepare the ground, prepare the Hamiltonian in the ground state of this initial Hamiltonian, which is an equal superposition of all the solution states, and this is sigma x. And then the final Hamiltonian you write. So this is your post function, right? So there was a z here, right? You have seen there was a z here, switched into sigma z. So I have not done anything. I just changed into the sigma z. This is your post function, and then you also put your constraint in your Hamiltonian as well, right? So these are your constraints. So 1 minus this one, I just put a square because you know, like this kind of a positive number, right? And then this is your second constraint, right? And then I put a and b here. So I choose a quite high, right? A is just a real number which is bigger than b, because we don't want this constraint to be violated. So this is you know, quite bigger, let's say. Okay, so you can choose. So that's how you, and then your final solution, final you know, the ground state of final Hamiltonian will be one of these, which is your solution. Okay, so you can find more. I mean, this is introduced in this paper, and then also this paper also have some of these elements, so you can learn about there about this method. So so I go next. Now this adiabatic quantum computation we can understand through single qubit, right? So I told you, so I have initial Hamiltonian, which is this sigma x. So this is my sigma x. I put a minus sign here, so minus here, and this is my control parameter, and this is my sigma z, which is final. So this is h final, and this is h initial, right? And when you get a, like you can diagonalize this matrix, it's very easy. So these will be the two eigenvalues. So clearly this is smaller because under root is always positive. So so this is a negative sign. So this is ground state. So this is ground state energy, and then you can write this is your ground state. You can find out the eigenvector. So this is the ground state where these theta are related to this control parameter in this way. And so basically when I am changing this like tau parameter, so initially I am in the ground state of this minus sigma z, which is this is initial point. And then I slowly change. So this is kind of rotation, because everything is rotation in case of qubit. So and then this is your final state. So it goes like this, and then ground state of sigma z is like spin down, right? And this is initial is equal superposition of spin up and spin down. Okay, so you start with the equal superposition state, and then you get into this. This is your solution, right? And when you change this, this energy changes. So this is the energy spectrum. So this is your ground, and this is your excited state, right? And this is the gap. So adiabatic theorem says that this change in this tau, right, must be the speed with which you change must be less than this speed, must be inversely proportional to this gap. So when the gap is small, you should make your change even slower, right? And when this gap closes, then like it and when you have a number of spin is large, right? So this gap is zero. This gap becomes zero, because this is called quantum phase transition. This is called quantum phase transition. Okay, so that's why this NP hard problems have this gap is very small. So like they are still difficult to realize in using this adiabatic quantum computation, right? So I go next. So this is basically in case of 8 qubit, you can write your program in terms of Hamiltonian, which is which people call is Ising model. So this is your H initial, and this is your H final, and then slowly you are changing your parameter from 0 to 1, this tau. So initially there is these qubits all are, or spins all are independent, and then you have external field in x direction, right, minus x direction, because there is minus sign. And then when you just slowly change it adiabatically, then there is a interaction between these happens. So you get this final Hamiltonian, right? And because you can always write your program, this program, like this Hamiltonian, this total Hamiltonian, this initial plus final, in this way. And writing program in this way is called quadratic, because there is quadratic term here. This is a quadratic function of these two operator. Quadratic unconstrained, because you put all the constraint here. Binary, because these are binary variable optimization program. So writing things like this is called quadratic unconstrained binary optimization. And if you want to learn more about Ising model, you can look at this book, which talk about quantum phase transitions, right? And also, of course, Ising model is very famous, so you can look at that. So this is the basic procedure of quantum adiabatic computation I told you, or quantum annealing. Right, so based upon this, so these are the two procedures. So I go next. So now I will tell you few other like combinatorial optimization problem, and and then I will, that's all I want to say. So combinatorial optimization, one of them is a quadratic assignment problem. So you have n facilities. Suppose you know, like maybe some you know, e-commerce company want to develop you know, like some facilities here. So they have some warehouses where they store goods, right? So they have n facilities, right? And they want to put them at n different locations, right? So the facility 1 can be put at one location, second location, and so on, n locations, right? So there are many possible combinations, right? And similarly for faculty 2, right? It can be put also here, here, or here, right? So you have n of them. So these are the facilities and these are the locations. And from facility I to j in a year, that much weight, that much goods, or you can volume or weight is a measure, that much weight transfer happens, right? Maybe 100 tons goes from faculty I to j, right? And you have, if the lot of weight happens, transfer happens between 1 and 2, you better want to put them close to each other, right? If a very small transfer of weight happen between 1 and n, right, you want to put them far away because that will not cost you much, right? So you have to minimize your cost, right? You have to the weight transfer between I and j happens wij, and then if you put the distance between position 1 and I and j is that much, right? So this is your total cost function, and you want to minimize your cost. So you want to arrange again, you can see there are many possible combinations can occur. So you use your simulated annealing, or you use your quantum annealing, and there is another algorithm also called QOAO, which I have prepared here, but there is another algorithm also, quantum algorithm. You can use that one to find out the solution which minimize this cost, right? And also, like, similar problem happens in finance, because you have n assets, right? So you want to invest in n different assets, right? So how you invest, right? How much money you will put in how much asset, right? So this is like an assignment also, right? So, and also it's a job assignment. So you also happens, like suppose you have n employees and n different jobs. So which employee you want to put for which job, right? So, or n machine and n jobs. So which machine you want to put for which job. So these all are, you know, like optimization problems. And when n is 1,000, right? Like a very big company, you have many employees or many machines. So, you know, this is very difficult, you know, to you know, get an optimized solution for this problem. So these are very practical problems. And then next practical problem is vehicle route optimization. Suppose you have, let's say, 10 customers, right? And is 10, and they ask, so each one asks that wi weight, right, to transfer. Like for example, this customer, you know, like one ask to transfer the weight from this 1 to 11, right? So w1. So they give you pickup point and delivery point, and then they give you amount of weight to transfer. Now you say you maybe have 2 trucks, right? So number of vehicle is 2, right? And you want to complete all these jobs, and you don't want to overload your you know, truck, because otherwise the police will catch you. And or you also want to, you know, like complete all these tasks. So you don't want to go to delivery point first, then pick up. It doesn't make sense, right? You have to go pick up first, then delivery first, and such kind of constraints. So this is called vehicle routing problem. So when you go, you order something from e-commerce, they do this kind of thing. So you give this one as an input information. You give a location of pickup and delivery points, and you also give the weight, and then you feed it to your system. You run it on classical computer, or you run it on quantum computer. Then the computer will provide you a map. So you provide a map for truck 1, and this is for truck 2, right? So truck 1 start from 2 to 9 to 19, 4 to 5, 7, 14, 15, and then it finish here. And then similarly start from 3, 8, and then delivery. So this is kind of vehicle routing problem, which is a, you know, generalization of traveling salesman problem, and it's have many great application. You can see that. And then next is a vehicle scheduling problem. Okay. So suppose you are running a transport company. So each vehicle have a one pickup point, and one it goes from two. Like this service has to be done from this place to this place for. So these are the trips, 20 trips to make, and they are in space, of course, x and y on the earth, and then there is a time coordinate also, because this trip time for 20 is it start at this time and end at this time, right? So you have to take these constraints, and then you have to find out that how like these 20 trips you want to complete by using less number of vehicles, right? And also you want to decrease your deadheading time. So deadheading time is like, suppose you start with so you take a vehicle which perform first trip 9, then between 9 and 10, so that much time is a deadheading time. So vehicle is staying there, is not doing anything, like Ola cab, right? So they, as soon as they finish one, you put one customer down, they want to take another customer, right? So they want to decrease this deadheading time, and also deadheading distance, because this 9 and 10, right, delivery point of, like a dropout point of 9, where is it, here, and pickup point of 10. So here, this distance you also have to minimize. So so you can see there are many possible combinations here also. So to minimize deadheading time and deadheading distance, and you can also use quantum computer to do that. So you start with the 20 trips and you can complete it with the 6 vehicle. So this is your solution, right? This is the timetable you get after running such algorithm. Then I go to another problem. Now suppose you have to design a supply chain network, right? Suppose you have 100, maybe 50 nodes, right? So this is n is equal to 50. So 50 cities, right? And imagine you are running a real airline services. So you don't, you want to connect all these cities. So one way of connecting is you connect every city by every city, right? So you will get a graph like this, right? So here one is connected directly to everything. So it's a direct connection. Okay. So this is, but you never see that the airline between two small cities, right? Okay, so you see only the connected airlines. So they work like this, right? And this kind of model is called P-hub model. So in P-hub model, you want to connect these 50 cities. So you say, okay, I will make these 2-3 hubs. The different airlines have different hubs. Like for example, Lufthansa have Frankfurt as a hub, and different airlines have different hubs. So you want to make 10 like main hubs, like maybe Bangalore or Delhi or Kolkata, right? So you want to make this, like 10 hubs. P is a number of hubs, and then another one is the small cities, spokes, right? You have seen this cycle tire, right? So you have like these structures. So these are called spokes, and this center part is called hub. Okay, so it's the same thing. So this model, you have to design this kind of network. So this is also supply chain network. So there you have a Wij, that weight transfer from city I to J, right? So from here to, let's say, here, right? And then what you will do, you will go first to your hub, and then the hubs are connected, all hubs are connected to each other. So you go from hub to another hub, and then you go to here. So you have a weight transfer, or weight can be number of passenger or number of cargo ships you have a weight, and then this is your cost, right? So cost to transfer from this to this, right? And from I to hub of I, and then HI to HI hub to HJ hub, right? This part, and then hub of J to J, right? And then this part is called discount, because traveling between hub is cheaper. So you have such kind of you have to minimize this cost and to get some supply chain network established. So this kind of thing is also combinatorial optimization program. You can also use classical simulated annealing or QoAO algorithm, or you can use quantum annealing, and or there are different other methods for to deal with these problems. So QPy AI is developing this chip, right, which have this classical optimization part and which have this quantum optimization part, right? So so we are developing this chip, and this is called this part is called Trion, and then the another part is called Optimus Prime, and all those results I showed you, they are obtained by us. I mean, although I give for more details some references, right? So all these results, like, I mean, these results and these results, this one, these are our results. So software part is we have developed, and then we are developing this this chip where we can do optimization, both classical as well as quantum, right? So that is all I want to say, and thank you so much.
Thank you, sir, for the wonderful talk. Now we should take any questions from the audience if anyone has. We have a question from Dr. Priya Nadkarni.
Okay. Yeah.
She says, D-Wave announced that, yes, sir?
As that they have 5,000 qubit system. Does it mean that it can solve a traveling salesman problem for the shortest path route, counting of 500 city or 70 city? Yeah, 70 city is possible. Yes, 70 raised to power 2 is almost 500. But there can be a smarter way, right? There can be smarter way to do this one, right? Like I just showed you one of the way, right? So our algorithms are based upon we are taking ideas from different part. We are taking idea from quantum. We are taking idea from classical algorithms. So you can I mean, certainly this is possible for 70 or 100 cities, but it can be even smaller. That is my answer. Also, I want to know how. So I think quantum annealing systems are kind of quite reliable because they repeat this many times. See, this is kind of error correction. So when I say this, right? So when I say this quantum annealing, this part, right? Repeating same thing many times. This is kind of error correction, and then you take majority vote, right? Because in error correction, what you do, you store your information in many qubits. So you repeat the same thing and then you repeat it many times. If quantum annealing run ideally, then it provide you the ground state in the end. But it don't run ideally because your system may jump from ground state to excited state, right? And then you get, rather than E0, you get E1. But if you repeat many times, so you will get E0 large number of times. So then you take a majority vote and then you say, this is my solution. And even though they are very close to each other, so their energy, even though you take this solution, the energy difference, means cost difference, will be very small also. So this is my answer.
Thank you, sir. She has asked a follow-up question. In the QPy AI processor, can processes based on universal quantum computing be designed?
So this chip is particularly for optimization. You cannot play computer games, you cannot play anything else. It's just do optimization, right? Because like your CPU or the computer I'm using to give this talk. So I'm using this CPU. CPU can do many things, but it cannot be great in everything, right? So this QPy AI chip, right? So this one is great in doing one thing, only one thing, and that is optimization. So it does do optimization. Yeah, for such problems.
We have a question from Mr. Vishnu. You may unmute yourself and ask.
Hello, Dr. Arun. It was a great talk. It was really inspiring to know that we can solve a lot of real world problems, optimization problems. I
Yes.
just wanted to ask what scale of problems were you able to solve till today? I mean, on this.
We have a customer from logistic companies which done lot of this vehicle routing optimization problem. So we cut their cost 60%. So if they are, like you can take a
using
1 billion,
this
yeah,
company?
using this. So $1 billion if they are putting in, company, and then you can see 40% is the money now they are putting if they use
And
this one.
yeah, may I ask what are the number of qubits in that particular task you're using?
Sorry, this is bit
That is
technical
okay.
detail. I cannot reveal that.
Okay, okay, cool. Thanks. Thanks a lot.
Yeah.
Great talk.
So if
We have one more question from Mr. Varki. You may unmute yourself and ask.
yes, yes.
Yeah, thank you, Dr. Arun, for the talk.
Thanks.
I just have a small question. Your processor that you shared, it's available in the market right now?
No, we are building it. We are building it.
Okay,
Yes.
okay.
So we have a solution. We are providing solution through clouds right now, right? And if because some of the companies they ask us to like shows great interest in developing this chip so that we can put this chip at their location. I mean, like wherever they are. I mean. So we are developing this chip, and right now they are accessing our solution through cloud. So QPI AI Cloud is one of the company QPI have. Which provide AI and such optimization solution through clouds. So they are using through clouds, yeah.
Yeah.
Thank you, sir. It appears we don't have any more questions. So I guess we can conclude the talk today.
Okay.
Dr. Arun Sehrawat, on behalf of IEEE-IISc Communications Society, I request you to kindly accept this plaque as a token of our appreciation from our end.
Thank you so much.